Okay, so the semiconductor industry is a ginormous industry. Just to put you into perspective, semiconductors, these class of materials that go into devices, devices go into systems. Basically, to give you an idea, if it was a country, the semiconductor industry would have the economy roughly of Germany. So to go from the raw material to devices, the process is very, very complicated. And so you need those enormous facilities we call foundries. So a foundry like this one cost about $15 billion to build. And in its life expectancy, it will basically create revenues of about $20 billion. So not all applications need high purity, high quality semiconductors. For example, in solar cells, we take the leftovers from the microelectronic industry, we remelt them to create lower quality ingots that are 80% cheaper, and we make solar cells. The idea is to keep the cost low instead of having very high performance stuff. So what we're trying to do is find synthetic approach to produce semiconductors. So we take quantum dots, semiconductor nanoparticles we create in solution, and we attach them together using a Velcro, a click molecule, a ligand, and we can make these very high quality films. And the idea is to see if they can allow us to get decent device properties. So the first step is to develop all kind of chemistry stunts. I'm an electrical engineer, so I call them stunts. And basically make spherical particles, cubic particles, star-shaped particles, nanowires, and we do size, we do core shell. And for me, it's always a little bit magic when my students do that. Then what we do is we attach them together. So we take these ligands, very long ligands, we remove them, we attach a short molecule, and then these particles attach together and form a styrofoam-like film. You know, you crush styrofoams, you have these balls falling off. So what we have now is we can see that over the years, we were able to adjust the chemistry to attach these quantum dots and nanoparticles and form 1D, a monolayer, 2D with a single nanoparticle thick, or attach them layer by layer and form a thicker film structure. But if we want to make a real device, we have to find more sophisticated stunts to make more sophisticated device structures than just a styrofoam-like film. So the idea, we went from the material, we assembled into films, now we need to go multi-layer, we need to put contacts, we need to do all kinds of things. So the first interesting thing that we discovered is that by putting different click molecules between the quantum dots, we can really control the electronic properties of these styrofoam-like films. So for example, here when we use a molecule that has this benzene ring in the middle, it will block holes, but it will allow electrons to go through. So very useful when you want to make devices. The other thing that we found is since we assemble them layer by layer, we can change the size of the nanoparticles as we assemble them, and that allows to bring the charge in the middle of the film, keep them there, and give much, much, much better performance as far as the material goes. Also, we can alternate type of nanoparticles. So for example, here we use PBS and PBSE. We alternate them, and we can make either light-emitting devices or we can make like harvesting devices by controlling the stacking of those layers. We can also play with the shape of the nanoparticles. We can go from spherical nanoparticles, or sometimes when we want better conductivity, we can go to longer nanowires and assemble them into structures like you see here on your right that basically we called nanoshag. So what we can do now is we can alternate layers of different shapes, different composition, different size, and with that we can create these synthetic-like films now that are really, really good solar cells. So for example, this is a solar cell device that can generate about 5% efficiency, so we're still trying to make them better. The beauty of it is you can put that on absolutely anything from glass, paper, your backyard shed if you want to, basically wood, any surface you can do that. So we're still trying to improve performances, but it looks like a promising alternative for low-cost solar cell harvesting. More recently, we also started doing composites, so mixing different types of nanoparticles inside the different layers of the film. And we saw, for example, that here by putting graphene flakes inside our collector, we were able again to improve even more the performance of the devices. Another important aspect, we talked earlier about transparent electrodes. So we also take metallic nanowires that we attach in these mesh kind of structures, and these are actually very, very good transparent electrodes, very flexible, they can be integrated on top of our structure, and we can see here, this is a figure called a figure of merit, and we talked this morning about ITO and FTO transparent electrodes, and we can see that if we tweak the conditions just right, those electrodes behave much better than those more conventional approaches, and they're also very cheap to produce. Now, we're not the first one to try to find cheap way to make semiconductor devices. These guys got the Nobel Prize in 2000 for conductive polymers. And the problem, there's many problems with these kind of approaches. They work, but they have several fundamental limitations. So for example, here, it's a visible light-emitting device made using just polymers. We made that in our lab. They're working good, but the electron transporting polymer that is there is kind of the weak link in the device. Also, the problem is they operate only in the visible range. So very good for producing light that you can see, but for some application, you want to move to other areas. So what we did is we formed now hybrid structures between polymers and our films of nanoparticles, and now we can make very good light-emitting devices like this one that now operate in the infrared and with much higher efficiencies. So these are mechanisms that we found to actually make some new optoelectronic devices at really, really low costs.
I have a question about the lead sulfide nanoparticles. In a state-of-the-art material, what is limiting the non-radiative recombination?
Well, usually it's defects. So in these nanoparticles, for example, what is the key problem is you have these surface states that you have around the nanoparticles. So a problem that you have is in solution, generally these devices, these particles are really, really efficient. The problem you have, because they have these long molecules wrapping the quantum dots, but when you remove them and put them into films, the challenge is now you free all these surface states, and then the performance can go down very significantly. So one thing you have to do after you cross-link is you have really to encapsulate the device to avoid the non-radiative recombination issues. So that's basically how we do that. But the short ligands actually help a little bit. And we see that some of the short ligands that we use to attach the films together are actually much better than others as far as protecting the nanoparticles and keeping the performance high.
Yeah. Thank you.
It's great, of course, to go for really low cost at these semiconductors for solar PV, but at some point, there's other stuff that you need for a solar cell. At some point, that is the thing that's going to cost a lot of money. So where's the minimum point where it doesn't really matter anymore how expensive our semiconductors are?
Well, I think it's a very good question. I would say the target right now, if you see right now a basic 12, 13 person, 14 person silicon solar cell costs about $300 per meter square. And right now it looks like for the market, it's fairly reasonable for at least developed countries. These kind of technologies, I think, have more promises in developing countries where the economy maybe cannot sustain $300 panels. But also, I think I don't think that these technologies will replace the silicon solar cells, because I mean they're really cheap. You can make a 12%, let's say, silicon solar cell in your kitchen for almost nothing. Now I'm not sure I would eat it in your kitchen after you did the chemistry there, but it's really not difficult. I think what these things will do is they be complementary. So for example, a problem right now with solar cells, let's say you go to a big store, and they want to put solar cells on the top. The structure of the building cannot support the weight of the panels. So, for example, these can be put on flexible, transparency-like sheets. So now you can make structures that are extremely lightweight. Or you can use surface area that you were not using before. I was mentioning the backyard shed before. So let's say you could go and spray paint your backyard shed with these kind of materials, then get 5, 6, 7% efficiency. Now you're using surfaces that you were not using before at very low cost. I think these will be complementary to more conventional solar cell technologies. I don't think they will replace them.